Hello, class.
Welcome, students. We're ready for a second part of the lesson here from Unit 5.3. We'd like you to open your binders up to page 232. That's where we are going to finish what we started last week, or last time I should say, on solving trig equations. We saw last time that to solve an equation, we're looking for all the solutions that satisfy the equation. And we did that by using some understanding of trigonometry. So let's see what we have here today with the 5-part A on page 232.
2 cosine 3x minus 1 equals 0.
And we're looking for those solutions again between 0 and 2 pi.
All right, now I think probably, Mr. Haas, at this point, there's quite a few of my students, and some of yours too, I'm sure, who are looking at this 3x with a little bit of trepidation.
That's right. Somehow that 3x makes it a lot harder when we just have a single angle there, such as theta. So maybe we should rewrite it so they don't get concerned here and think about what would happen if it was just 2 cosine theta minus 1.
Okay, so you've kind of done a little substitution move and you've let theta take the place of 3x.
That's right. This angle x is just going to be 3 times smaller than theta, or theta is going to be 3 times bigger than x.
And now shrinking and multiplying a trig function on the x by a number, that makes it wider or narrower? What does that do?
Well, when we use 3x, that changes the period. We saw last couple chapters that you're dividing the normal 2 pi period by 3. So now it's going to be 1/3 as large as it was before.
So instead of taking 2 pi to get through all of its wave, this is only going to take 2/3 pi.
That's right. So we're going to get actually more solutions than you normally would expect as we go around. But I think we'll see that once we get into the problem here.
All right, so let's just solve this one and see if that helps us get into a good position to be able to come back to the more complicated original.
That's right. Since 3x is actually inside the cosine, we should solve for the cosine first and then deal with the 3x.
All right, this is like a composite function.
Yeah, exactly.
For the people who remember chapter 1 and 2.
They remember that well.
All right, so now here, this we can solve. We're going to put the 1 on the other side and divide by 2, and we can say real quick that cosine theta is equal to 1/2. That's easy math.
That is easy math, so that's great. And we know in our unit circle how to deal with a cosine that equals...
Cosine is x on the unit circle.
1/2.
And so when we get an x value of 1/2, we're either up there at pi over 3, or we're down there and we've gone down pi over 3, but we think about that coming the long way around as 5 pi over 3.
Now at this point we recognize that we're not done the problem because the major part of it is the fact that this angle theta is actually 3 times the angle x that we're looking for.
Okay, so this means that what we just solved is only going to telling us 3 times too much.
That's right. So let's go back and use our substitution that you mentioned and get back that 3x.
All right, so theta was actually, that was 3x. That's where that came from. That's where we generated that. And so now if I'm looking for just x, I need 1/3 as much.
That's right. We're going to divide by 3
Divide by 3. So that's going to get me pi over 9. That's not any angle we've done anything with.
That's right. Because we're dividing by 3, we're picking up angles that are a lot smaller as we compress it. So pi over 9 is in the first quadrant.
Oh, we've compressed. Even though it was a multiple, we've compressed.
That's right. And 5/9 is a little bit more than 1/2. So that's going to be right about here. So this shows us there could be more solutions as we move around the circle.
And since we only been using 2/3 of pi, our normally we would be using 2 pi, we're only using this much here because we've been compressed like that.
That's right.
So now we found these ones in here, but we also need to keep going and talk about the same ones that might happen in the next third or in that last third.
That's right. There will be, since there are 2 solutions in this section, there'll be 2 more here and 2 more here. We're going to be looking for 6 solutions altogether.
Okay, so if I come back to this original one where I ignored that.
That's right. Come back to theta.
Come back to theta. this would involve going more than once around the circle.
That's right. So if we think about the circle being 2 pi being in thirds, the same as
6/3.
6/3.
Okay.
We can go around the circle and come back and get 7/3
Yeah,
again.
so if I add 2 pi to this, I would get 7/3 pi. And if I add 2 pi or 6/3 pi to this one, that would be 11 pi thirds.
Excellent. So at this point, since we have more angles that have a cosine of a half, we can now divide by 3, pick up more solutions.
And get 7 pi ninths and 11 pi ninths.
So when you have a third and you divide by 3, it's the same as taking another third. Third times a third is a ninth. Great. Now we're not done yet, because even with 7/3, even with 7 ninths,
That
which
was
is a
this
little
part.
bit
This,
less than 1,
yeah.
and 11 ninths was a little bit more than 1, we still have more room where we might have solutions.
We haven't done anything with the last cycle that would be completed in the original constraint of 0 to 2 pi.
That's right.
So we add, okay, so we've been adding 2 pi, a full circle again back here,
That's
and
right.
that was 6 pi thirds. So 7 pi thirds plus 6 pi thirds
Let's put it maybe underneath here.
is going to be 13 pi thirds.
All right, so we pick up another one in the thirds category.
And then 11 pi thirds plus 6 pi thirds is 17 pi thirds.
So class, even though these angles here are outside of our range, we still haven't divided by 3 yet, and so that's why we need to pay attention to them.
So we keep going even though it's past 2 pi, because we know that these are all going to be compressed
That's right.
by a third. All right, so now that means that we can turn 13 pi thirds into 13 pi ninths, continuing our dividing by 3, and 17 pi ninths.
Excellent. So a lot of solutions here between 0 and 2 pi because of the compression of our cosine wave.
And I can tell that this is a good place to stop, because all the way around 2 pi would be 18 pi ninths.
Ah, very
so
good.
this is just 1 shy of that, 1/9 shy of all the way around, and we haven't gone over our original constraint of 2 pi.
Sounds good. Looks like we've got every solution we need for this particular problem.
So these two were the ones that would have occurred to me if I had only done just that little bit, but I needed 3 times as many as that.
That's right.
Because the whole thing has been compressed by a factor of 3.
Excellent. We'll do one more example like this, only this time, instead of compressing it, we'll go the other direction so you can see what happens if the number in front of x on the inside of our function is 1/2. So now
Everybody
you
got
have
that?
that all down. Hopefully you've taken notes on that or gotten the main points down. You're ready to join us in part B, where we have 3 tangents. And I'll let you write this in black. The angle here is 1/2 x. And then we have a +3 equal to 0.
I like how you let me write that angle there. That stands out as the troublesome spot.
Exactly. That's the part that may give you trouble. But again, remember, you can think of it just as a single angle. You can group it together in your mind as an angle theta.
You want to call that theta?
Let's do theta. I think the students are happy with that.
Let theta equal 1/2 x. All right.
Again, our range I'll put over here. We're looking between 0 and 2 pi.
All right. Now see, now there is an easy problem that I can solve without
That's
a whole
right.
lot of trouble.
We don't do any factoring because it's not quadratic. It's just a linear equation.
Move the 3 to the other side where it's negative. Divide by 3. It's -1.
Very good. So when you have a single function, you can isolate it and then solve it from there.
And now we need our unit
Let's
circle.
grab the unit circle. We're looking for tangent. How do we find tangent?
Tangent is slope.
The slope is like the y over the x, the rise of the run. We know +1 slope is with our pi over 4. Our case then, we want the opposite of that. We're going to use the second and fourth quadrants in order to get a -1 for our tangent.
Okay, so it's not 1/4 or 2/4, but 3/4 up there.
Let's go to 3/4 of pi.
And then we also need to have the equivalent of -1/4 pi. And so all the way around would be 8/4 pi minus 1 is 7/4 pi.
Okay, so since 2 is 8/4, we go back to 7/4 to get to the fourth quadrant. Very good. Now we have to remember that theta is not the final answer.
Oh
need to
yeah, we
find
cheated, I
x.
forgot. All right, so that was actually half x that we substituted in there for theta.
That's correct.
So now if I want to find x, not just half x, I need to double all of this.
That's right. And before you do that, just so we can see what might have happened if we had gone around the circle again to find more places where tangent is -1.
Okay.
It might be interesting to students, since we did that last time, to see what would happen again. So since you said that 2 pi was 8/4, if we go around again, we would come to 11/4. And if we were to take 7 pi fourths around again, we would come to 15/4. Now, I'm not sure these will all be useful, but I want to have them here so that we can check.
That's good practice for in case we need to go more than all the way around.
That's right. Let's give it a shot now and see if we can solve for x.
All right, so we're doubling what we got in order to double half x to get to plain x. So that means if you double this, timesing by 2, the 2 and the 4, that fraction will reduce.
Do I multiply by 2 on both the top and the bottom?
That would be multiplying by 1. Because
you're right.
2 over 2 is 1.
Okay, so I can't do that.
Yeah.
So which one do I multiply by 2?
So if you multiply on the top by 2, that would be 6/4.
6/4.
Which reduces.
I got you. 6/4 is the same as our 3/2 pi.
3 pi.
Wow, we're already around to 3/2 pi.
We're close to the finish line here.
Yeah.
And so now if I try this one.
If I double that one, what am I going to get?
14 pi fourths.
14 over 4. That's the same as 7/2.
7 pi over 2. Wait a minute.
Yeah, if I go 7/2, it's 1/2, 2/2, 3/2, 4/2, 5/2, 6/2, 7/2. I've gone way past 2 pi.
Yeah, so that won't fly.
That's right. Based on the range that they gave us here to solve for, we're not going to use that one.
Let alone
these
any
are
of
not
those
going to
huge
be
ones there.
needed either. So instead of getting more solutions than before, we're only getting half the solutions that we normally would have.
There you go. So when we did 3x on the problem before, we needed 3 times as many solutions.
That's right.
When we did half x, we only needed half as many solutions.
Half as many solutions as you normally would have in a normal period. Very good.
All right.
The one thing we should point out, I guess, is that tangent's period isn't the same as sine and cosine. It normally is just a period of pi.
True.
So in this case, it just so happened that we were using, within the 2 pi period, we're still only getting one solution by doubling it.
So it was a good test to us to keep going in case we needed them.
Yep. I think we're ready to go to the next type of problem here. So class, hopefully you've taken some good notes on how to deal with multiple angles. And you like Mr. Murphy's method of substituting when it gets tricky on the inside of the function, just using theta to represent that more complicated angle. Now let's take a look at what happens when we have multiple powers of sine and cosine. So we're going to step it up here and look at number 6, part A. What happens if we have cosine cubed, and we want to know when it equals the cosine of x, and we'll use our normal period of 0 to 2 pi.
All right, so I'm looking at this and I'm thinking there's some student out there who says, aha, let's just divide by cosine.
That's a dangerous thing to do.
Tisk,
Why
tisk.
is that? Because
You might divide by 0
what if cosine was 0?
and you might eliminate some solutions.
All right, so we don't want to lose any solutions. So we want to do, like in any polynomial, we want to try to get it equal to 0, like we did with the quadratic
Quadratics
functions.
are a kind of polynomial.
Let's move everything to one side and get 0 by itself.
Love to have stuff equal 0.
All right, opens up some things. Now we have a common cosine in both of these terms.
Let's pull that out.
So getting things equal to 0 and factoring is a great technique when you're solving any kind of equation.
Okay, so now we've already told them about this trick. This isn't going to go away. We're dividing by cosine here. We're factoring it out, so it's -1.
That's right, class. Division is the opposite of multiplication, so you can check your work here and make sure you're getting back what you started with.
Okay, so And we've got two things being multiplied equal to 0, our favorite thing.
That's right. We might want to point out just one little thing that's interesting
Ah.
here, that sometimes when students see an a squared minus a b squared, they see a difference of squares.
That would be ideal if they saw that.
They can then do what?
That factors into first plus second times first minus second.
Okay, so we could factor it further. We wouldn't have to do it here, but it might be nice just to illustrate something you can do when you're factoring is you can take the second degree term and break that into two more linear factors. So you can see that we can actually come up with 3 factors, which makes a lot of sense when you think about a third degree.
We had a cubic kind of beginning,
Cubic
so we would
equation.
expect 3.
It's nice to find the 3 different ways to get equal to 0.
And then we can write that out long ways and say that either cos x equals 0, or cos x equals 1, or cos x equals -1.
All right, so I've already got the unit circle ready to go to see what angles will produce these 3 results.
So when is, on the unit circle, when is my x equal to 0, left and right on the center line?
There's 0.
That happens up high at pi over 2,
Up north
and down south.
at the South Pole, 3 pi over 2.
All right. Then over there at the East Pole, I made that up.
Cosine equal to 1.
Cosine is equal to 1 at 0, which
Okay.
is the same as 2 pi, but we're not allowed to call it that
So
this
we're
time.
including 0, but not including 2 pi this time.
Can't quite make it there. And then over there on the west, we've got pi.
All right, so it looks like we came up with 4 solutions that would all work if we tested them here. Cosine cubed would be the same as cosine at those 4 places. That makes
And if
a lot
we
of
had just
sense.
said here that cosine squared equals 1, take the square root of both sides, you'd still get plus or minus 1.
That's a good point. If you use the square root method, just be careful to get both square roots when you take the square root of 1. That's a good point.
But our students are careful, and they always know when they square root to add the plus or minus sign.
That's correct. We're good to go with number 6A. Let's move on. You guys there, take a breather while we erase and get your pencils ready for another exciting trig equation. This one's going to involve some mixtures of sines and cosines. We saw that the other day, and hopefully you remembered some of our strategies. But if not, Mr. Murphy's back with his bag of tricks again to help us out. 4 sine cubed x, 4 cosine squared x is equal to 1 plus 3 sine x.
Now, hopefully, as a student in this class, your gut instinct has been getting refined here from
Yes.
doing some of these problems, and you say, I don't have a sine cubed identity in
that's
mind,
right.
and I don't have a sine identity in mind, but I do have a cosine squared.
So this is the one that is the red flag here. It sticks out in our mind. We know some things about cosine squared.
Immovable, immovable, movable, alterable, changeable,
Okay.
malleable. We can do something with that.
And he's also kind of the oddball, isn't he? Because we have all sines except for that one cosine.
So we'd
there.
love to get rid of him.
All right, class, what do you remember about cosine squared? What do we know about cosine squared? Back in the unit circle, we know the Pythagorean identity. When you have cosine and sine, the hypotenuse was 1. So
Sine squared plus cos
Cosine
squared equals 1.
now we're going to go backwards because we want to get the cosine squared by itself. So we want to think hypotenuse squared minus the leg squared. 1 minus sine squared is the same as that cosine squared.
All right, so I'm going to go ahead and take what you just did there, Mr. Haas, and
All right.
substitute it into your red flag area there.
Substitution is one of those powerful methods in math where if we find something that we know equals something else, we can replace it. At first, this may look more complicated than we had before.
Oh, thank you.
All right? But it's going to actually help us. Like Mr. Murphy said previously, sometimes making things look more complicated can actually make things simpler later on. Let's see what happens.
All right, so we need to distribute that and get 4 minus 4 sine x. That's what's going to happen in that part.
Okay.
The rest is unaffected.
Go ahead and square this one.
Thank you.
Cube that one over there.
And cube that one over there.
And because that is important to notice that there's different powers here of sine, and that's going to be important to us. We try to put those into some kind of nice organization. We want to get a nice standard form.
Yeah, so when we have like polynomials or anything with powers like that, how is the right way to write that out?
Well, it's helpful to get it organized so the highest power comes first, then we work our way down to our constant, and eventually, we'd like to have 0 on one side.
Okay, so we've only got this one here for our cubic.
Let's keep that one up front.
So then we should go looking after that for squared.
Okay,
We've got
one of those.
Only one of those.
There.
That's pretty straightforward. And now we go looking for ones with one exponent.
This one you want to move over to change the sign of it.
The SIGN.
Exactly.
It gets tricky here in trigonometry. All right, and then for plain numbers, we already had 4 over here, and we bring a 1 over where it makes it negative.
Ah, there we go.
So that means that it's just 3.
Very interesting. So we've got not just 3 terms, but we've got 4 different terms here in our cubic polynomial.
And really, really common when you've got 4 terms, factoring by grouping ought to be springing to mind for some people.
That's right. That's a nice way to factor, because we can't take, some people like to take a sine x out of everything, but this one doesn't have a sine.
That won't work.
But if we look at just the first 2, what's in common there?
We got 4 and sine squared, at least, in both of those. And then here, something's going to get together as well.
Very good. So if we look at these 2, we see that there might be something in common, even though it may only be a number or something.
Yeah. So now if we take these here, the greatest common factor of the first 2 is going to be 4 sine squared. And what are we going to be left with when we pull that out of here?
Okay, so if we have 4 sine squared, we have to multiply by a sine to get sine cubed. So that must be just sine x.
Just sine x. And here we divided by exactly that.
The same
Anything
thing.
divided by itself is 1.
1. Okay, so that's important that we don't skip the 1, because this times this gets us back to what we started with. Great.
All right, so now our goal here, since we've done this, is when we factor, we ought to end up with this same thing in parentheses if we're doing it right.
We're hoping that we'll have the same factor. Let's see if we get something like that.
In order to do that, if I could try to pull off a -3 out of here and not just a 3.
Oh, I see. So if you just factor out a +3, this would be a negative sign, and we want a positive sign. That makes sense.
Helpful to try to have a goal to shoot for. Okay, so if I factor out -3, I've pulled off the -3 and I'm just left with sine. And now +3 divided by -3 is -1.
That's right. A negative times a negative makes that positive. Very good.
All right, so that worked. We got the parentheses are the same. And again, we can do the opposite of the distributive principle.
Oh, so you're saying that when you have the same thing here that you have over here, you can factor out what's in common in each of those boxes there.
Which is sine x minus 3. So we end up...
Sine x minus 1, you mean?
Sine x minus 1, thank you. So we got 4 sine squared minus 3 as one item.
Okay.
And now they're the common term, sine x minus 1.
So you're saying that when you pull out the sine x minus 1 from both of these, then the only thing left is your 4. Yeah, that makes sense. 4 sine squared minus 3.
And that worked great because now we've got 2 things that when they multiply equal 0, so either the first one is 0 or the second one is 0.
All right, go ahead and set those equal to 0. I'll get out the unit circle and we'll see where our solutions are.
All right, so that's 4 sine squared x equals 3 or sine x equals 1. And we can simplify that. Divide both sides by 4.
Okay, so sine squared would have to be 3/4.
And now this square, this one, it would be nice to get rid of that square.
Yes, we need to get rid of the square. Let's take the square root of both sides.
Take the square root of both sides, and I'm definitely going to remember my plus or minus.
Sounds good.
Square root of 3, I can't do a lot with that. That's just going to stay the square root of 3. But the square root of 4, I know,
There's
is
a nice
2.
whole number. Good.
Yes.
Oh, and square root of 3 over 2 is one of our recognizable
Things from
numbers
the
on
unit circle.
All
right, and we need all of them.
That's right. We need every quadrant because we're going from 0 to 2 pi, I believe. Let me go back and check that. Yes, we were looking between 0 and 2 pi for our solutions. So we're going to go around and see where does the sign, that's the y, equal the
pretty
plus
high there.
or minus. So it's near the top of the circle here. When cosine is a half, the sine is the one that's the square root of 3 over 2. So we want
That's that high angle, which is pi over 3.
pi over 3.
Okay. And now we need another place where that
Maybe
would...
let's put that underneath here just in case, because the other part's sine 1. Maybe the students might be confused by that. And now if we look at where the sine of x equals 1, I know there's other answers for that first one, but let's grab this one while we're...
So our y value is up high.
Way up the top. Pi over 2 is the only place between 0 and 2 pi once around the circle. So now we have room to put the other ones here where the sine in the other quadrants. Let's go over to quadrant 2, 2/3. Notice the sign class is positive in both of those. And then for our negatives, we'll go down to the third and fourth quadrant where we have our 4/3 of pi and our 5/3 of pi. So all the thirds there, they're close to the y-axis, have those plus or minus square root of 3 over 2.
Do you make people write those in exact ascending order?
Well, as long as they have the right answers, I would be happy, but that certainly makes it easier to read.
All right, so that would mean then that we would have a third and a half, and then 2/3, and then 4/3, and then 5/3.
I see what you mean. You're saying that when we combine the solutions from this part with those four, it's
that
nice
one
to
has to
see where it fits in.
there.
Yeah, that's nice. So there we see that there's 1, 2, 3, 4, 5 different solutions. We're making great progress here. Hopefully you all have taken good notes here on how we factored by grouping. That's a great skill to have in algebra as well as in trigonometry. And we made good use of that as well as using our Pythagorean identity early on to get all the signs together there.
A lot of different skills go into this.
Now we're going to do a little change here. You've been noticing that by coincidence, all our sines and cosines have been things that we memorized on the unit circle. In actuality, there are many other angles and many other sine and cosines that we don't have memorized. So we're going to be using our calculators in this next section to show you how you can solve equations that are much more complicated, where algebra is not going to be the answer to all of our problems. So here's the good news for those of you who like technology. Take out your TI calculator if you have it with you. Make sure you set the calculator to the mode, under the mode button, the third one down on the left says radian. Make sure you press enter so it's dark on radians instead of degrees. And we're going to continue to find solutions using radian measure. And this time, we're not going to have to do as much algebra work. We're going to let the calculator help us to find those solutions by using this technology. So the first thing you'll notice in this problem, class, is that even though we have sine and cosine, one of the signs is being multiplied by x.
Whoa.
And that changes things up. It mixes a normal kind of linear function with these different trig functions. So here's the good news. Instead of having to isolate this x or that x, which one would you solve for? We are simply going to take the entire left side here and put it into our calculator as the y1. So if you would write y1 equals that entire function, we'll be able to go to our calculators, press the y equals button, and we'll be able to type in this entire left side of the equation. So I'm going to type in 2 times cosine x. You'll notice that we have to close off the parentheses on the calculator around the x. Normally you don't have to write that, but the calculator would like to see that. And then plus 2 times x times the sine. And again, the parentheses will come up and you will close off the sine as well. So at this point, you have something that looks something like this, although these on this particular calculator are not necessary. They'll just be next to each other, but that's exactly what that means, multiplication. And now we're going to look at the graph of this function. Now, does it say, Mr. Murphy, what range they're looking for?
0 to 2 pi.
All right, the normal 0 to 2 pi. Is there brackets?
Yep, don't get to 2 pi. Just
all right, keep the 0.
Bracket on the left.
Okay, so we're going to keep 0 and 2 pi. Now, what this means in the calculator class is you're going to go to the window button, and you're going to be looking from x equals 0 2x equals 2 pi. And when you put 2 pi
So
in...
x min, is that what it's
Yes,
called?
right. The x min is 0.
X min is 0.
The x max would be our 2 pi.
And you can actually use 2 pi on your calculator there.
That's
instead
right.
of having
The
to-
yellow pi button there will get you pi.
Yep.
And once you put in the 2 pi, it'll change it to 6.28. So that's the same thing. And now we're going to set up a scale. This is kind of an arbitrary scale that we'll use. Generally, pi over 4 is a good scale to use there for the scale, because that divides up the unit circle into nice sections. Now, once we have that, we also have to put in the y values. The normal sine and cosine stay between 1 and -1, but this is going to be more involved in just going from 1 to -1. So let's go from -4 to 4 and see if that's adequate. Once we press the graph, we'll know whether or not we need to change our window. So we're going to go ahead and graph that and take a look. Sure enough, the graph starts near 2, it increases, and then it decreases, and it goes down quite a bit. In fact, it goes a little lower than -4, so let me change the window
Okay.
so that we go down to maybe -6 on our y minimum. And our y maximum, 4 was okay. I think it covered the entire picture. So when it comes to the y values, class, you just have to look and see how much of
Trial
it
and
you're going
error.
to need. That's right. In fact, it turns out that -6 wasn't enough if I want to really see it. But you know what? I'm not going to worry about that because we're not interested in where the sine value reaches -6 or -8. We're interested in where the whole function is going to equal 0.
Oh, the zeros of this monster function here.
That's right. All we have to do is figure out when is it going to equal 0. We can see the zeros by looking right along
Where it crosses the x-axis.
the x-axis. That's right.
And the calculator can tell us those numbers precisely.
That's right. We notice from the graph, and in case you can't see it on your screen, I'll draw the graph here. There are 2 places where the graph crosses over, and we're going to show you how to find those easily on your calculator. You don't want to just do the trace button, class, because when you trace, it skips different points, and it might skip over the places we want where it equals 0.
That would tell you the general vicinity.
That's right. It would give you a good approximation, but we're going to try to be really accurate. So we're going to press second calculate under second trace, and we're going to go down to button number 2, which says 0. So once you press that 0 button, the calculator is going to ask you 3 things. It's going to say, what's the left bound?
Okay, so
So I
something
need to
on
get
the
to
left
the left.
side. Yep.
So I'm going to arrow over until I see it flashing to the left of that point,
Okay.
and I'm going to press enter.
It's kind of a little spidery thing, actually, isn't it?
That's right. So it finds that one
Little
spot
spider.
there.
Yep.
And then we're going to try to get to what says the right boundary. So we're kind of trapping the answer between 2 different points. So once you get below the axis, press enter for the right boundary.
And then a guess?
That's right. It asks a third question. It says, what point do you want between those? And it really won't matter as long as we go between and press enter again.
Save yourself some computation time.
Oh, look at
Good guess.
that. It tells exactly when it's 0 when x equals, and we'll write that answer up here. X equals 2.798, and it keeps going. It's an irrational number. So they say how accurate.
2 decimal places.
Oh, we only need 2 decimal places.
So
So since
280.
the third one is 8, I've got to go up on the 9. So how do I go up on 9? I have to go up to approximately 2.80.
All right.
So there's our first solution. The second one is further to the right. Let's do the same thing again.
So you're going to take a left bound and a right bound, and then you're going to take a guess. and
Right
it's
in
gonna-
between somewhere. All right, let's give it a shot. So we're going to go second calculate down to number 2, 0, press enter. You're flashing at the old one right now, so we need to go right arrow to get over there. The other thing we can do is sometimes just type a number in if we can see where it's going to be. So if you could see where it was, I'm going to keep just arrowing over there a little bit more for you. So there we go. I'm finally getting over there. It's a little slow. Hopefully I haven't gone past it.
Action shot right
Action
here.
shot. There we go. Okay, so 5.8 is on the left.
Okay.
I'm going to press enter. I'm going to get over to the right. So we're almost to 2 pi, so we have to stay within the bounds there. Finally, do our guess. Press enter the third time, and it tells us 6.12125. Of course, they want us to round to the
2 decimal places.
2 decimal places. So since this is a 1, we'll stay at
612.
6.12. So we have 2 perfectly good solutions here. And the good news, probably you appreciate it, we have to do any algebra work. We let the calculator do the work for us in finding those solutions. Now, we don't want you to always use the calculator to get the answer, but you can certainly use it as a check. One of the reasons we don't use the calculator all the time is these are only approximate solutions. When we use the unit circle, we're getting more exact solutions.
So sometimes we can get things that have precise answers.
That's right. And those precise answers can be useful in just understanding the relationships between our functions. But certainly in a practical level, these kind of solutions are used in the real world, and they want to know where something is going to have a solution.
All right, one more like that?
One more like that.
7b says that x tangent of 0.5x equals 2x minus 1.
So this time, class, we're going to illustrate a second method using your technology. Instead of getting it equal to 0 like we had the first time, and by the way, we could make it equal to 0 if we wanted to.
Move everything to one side.
That's right, but instead of doing that, just to show you a second alternative method that might be faster, we're going to take each side of the equation and put that into the calculator as its own graph. So we're going to press y equals again, and we're going to clear out the old function that was there, and we're going to put in this new one, x times tangent, and notice parentheses will come up, put in 0.5x and close the parentheses. That takes care of the entire left side as your first equation. Then we go to the other side, which is a simple linear equation. You probably know what that's going to look like. Arrow down to y2 and put in 2 times x minus 1. And when we press the graph this time, we will see a picture of each of those functions between 0 and 2 pi. The first one is our typical tangent. It's got an asymptote. And the other one is our line that's crossing over crossing over the tangent graph. Now,
so your 83 is drawing the asymptote because it's trying to connect positive infinity and negative infinity.
Exactly.
Someone
right.
with an 84 silver or one of those schnazzy ones will not have those asymptotic lines.
Okay, so either way, we're not so much concerned about that part of the graph. Now we are concerned about 0 to 2 pi, so check your window to make sure you're still from 0 to 2 pi on the x, the min and the max. And this time, since our tangent function goes upward towards infinity, we're going to increase our y min and max so we don't miss any intersection points. We're going to increase our minimum down to -10 and our maximum up to +10, so that when we look at the entire graph, we're making sure that we're picking up each solution that would be between 0 and 2 pi. So I can see very clearly now that the graph, I'm going to switch markers. This one's getting a little bit hard to read. So we can see that the graph, and again, we're starting from 0, so you're watching it from 0 towards 2 pi. And you can see how the tangent function is going upwards towards infinity. You see the vertical asymptote coming down and then it coming back towards 0. And you see the linear function coming through and crossing over. It looks like there might be 2 solutions where the left side would be equal to the right.
Yeah.
So the button we're going to use for intersection, to find those 2 points of intersection, is to go second, calculate number 5. Number 5 is the intersect button. When you press enter, it asks 3 questions again. Here's the 3 questions. The first thing it asks is, what's the first curve that we want to use in the intersections? Now the good news for us is we only have 2 curves, so we're going to pick the first one. Now you may not know how to select it, so let me arrow over here away from the asymptote. I think I'm going to go to the left, so arrow to the left here. Okay, once you see it on this curve, flashing on the curve, that's
the little spider walking on the curve.
That's right, that's one of the ones we want. So press enter. It will automatically jump down to the next one, which is our line, and we want to use that one, so press enter to get that. And now we have a choice. Which of the 2 points do we want it to get from our guess? Well, since we're already close to this one, let's just go ahead and get close to that point and press enter, and it will tell us 2 numbers. It will tell us an x and a y. You're noticing that we are only solving for x. The y is not what we're asking for in this problem. So we're going to concentrate on the x value at our first point of intersection. is x equals 1.959. We're going to have to round that eventually.
To 2 decimal places.
2 decimal places, so that's going to be approximately 1 point. Again, the 9 tells you go up to 9.6.
Okay.
There's our first solution. So even though the y is equal to 2.918, that's not our concern. We're solving for the x value. The second point of intersection is further to the left, so we're going to go through the same game again. Second, calculate. Number 5, intersect.
Pick the 2 things that are intersecting.
So right now, you can't tell the difference between the 2 things because they're right on both of them. So we're going to go a little bit to the left here so you can distinguish them. Okay, we've got the first one, enter. The second one, enter. You might wonder why they even asked the question about which 2. Well, that's because the calculator could hold more than 2 equations, and then you'd have to choose which ones you wanted. In our case, we've only put in these 2, and so it's very simple for us to choose those. Now, the last thing we want is not this point again, but the other one. So we're going to need to arrow over in our guess close.
To 0.5-ish.
Yeah, you don't have to be exactly on it, but close to that one. And when you press enter, it tells you this other one is equal to x equals 0.58947. If you were in a different mode, such as degree mode, you'd be getting a whole different set of answers. So if you're not getting the same thing that we are today, check your mode button, make sure you're in the correct mode. Again, we want the x value to 2 decimals, so we'll round up to around 0.59. So that makes sense. So this is close to 0 at 0.59, and this one is
a little more than half a pi.
Yeah, a little more than half a pi. Very good. So we showed you, class, 2 ways of solving using the calculator to solve
zeros and
intersections. And the intersection.
Okay.
Now, I am going to make one comment about that. When you compare the 2 methods, there is a little disadvantage in the second method that we used. And here's what that would be. If these 2 things happen to intersect outside the range of my window, I might not see it if I didn't make it large enough or small enough. In the other method, when you move everything over and get it equal to 0, you know that 0 is always going to be along this strip right here.
So you don't have to try to guess about the y range.
That's
you can just
right.
stay close to 0.
As long as you stay close to 0, you'll see those x-intercepts. So that's why it might be an advantage to do the algebra work of moving everything over, risking maybe making an algebra mistake, but at least coming up with something where you're going to be able to see the zeros. So if you're having trouble finding the intersection points, switch to the other method by doing a little bit of algebra work and then getting it equal to 0, and that will help you not miss any solutions. But we've done a great job with the calculator. Let's go back and finish off this page if we have some time left. We are going to finish off with some problems that may be review for you. The first one is sine squared x minus sine x times cosine x equals 0.
Okay, so that looks a little bit entangled there. We've got our immovable pieces buttoned up against each other.
That's right. So we would have a hard time saying, oh, let's just change sine squared into 1 minus cosine squared.
That wouldn't help.
Because we still have another sine left here. And we can't take the cosine out when there's only one cosine. That would be difficult.
But we do have sine in common.
Oh, that's right. When you have 2 terms, you can see that they share something in common.
Should I go with that?
Let's factor out the common term. That's a good method for being able to get something a little bit simpler than what we started with. Both of these factors seem to be fairly simple. They're both first degree.
Okay.
So let's try setting each one equal to 0.
Sine x equals 0, that's not too bad.
That'll be easy to find.
But sine x equals cos x, that's a little new.
Oh, I see what you thought there. You said if sine x minus cosine x is 0, then they must be equal to each other.
Well, I could, just move this to the other side of the equals.
Oh, the equal sign.
Yeah.
Okay. So that's interesting. Let's look at our unit circle. When does sine x actually equal cosine x?
Well, on the unit circle, sine is my y value.
Okay.
So I can kind of think of it this way.
All right.
And cosine is my x value. So those, when y equals x, that's when
okay.
those two will be equal to each other.
Yeah, we know in the first quadrant that x and y are equal.
Yeah, see, there's the line, y equals x.
Yeah, there's y equals x right down the middle, hits the unit circle at our friend pi over 4.
Okay. So that happened there. There was an x of pi over 4, but there's another spot down there in the third quadrant.
Oh, that's right. Two negatives, when you divide them, cancel out and gives you this, or when negatives are equal to each other, I should say.
Yeah.
We have 5 pi over 4.
Okay. And then our y value being equal to 0.
Y is the y-axis equal to 0. There are two places there, it looks like.
Way back at the beginning.
So we have
And
0, which is
way.
included. We have pi, which is included, but not 2 pi, which has been left out.
Okay. So this one we solved even though we made kind of a novel, interesting thing out of the second term, but still factoring it made it something that logically we could think through.
We could solve it by setting equal to 0 and look at the sine and cosine. Now, if this became more complicated, while you're writing down the 4 solutions there to the final answer, we'll talk about maybe one more strategy that a student could use that didn't recognize when sine and cosine were equal.
Yeah, what else
They
is there?
could turn this into a tangent function.
Oh, divide both sides by cos right there.
If we divide both sides by cosine, then we have tangent x would be equal to 1, and sure
There's
enough,
that slope of 1,
we
rise
have
and
a
run are the
slope
same.
of 1. That might remind you that why we want to use pi over 4 and 5 pi over 4.
That's good for
The only danger we said dividing by cosine was, what if cosine was 0? But fortunately for us, cosine is not one of the factors that equals 0. So we're safe in this case to divide by cosine.
All right. Everybody got that one there? Got those 4 solutions?
All right, you guys have done a great job taking notes today. We're almost done. We've got one more to show you, and then we're going to ask you this weekend to work on the homework assignment that uses this section to finish the section 5.3 homework problems, and to be prepared next week as we move forward when we'll be back in town with you all. So here's the last one, Mr. Murphy. We've got 2 cosine x minus the secant of x, and that's supposed to equal 0.
And are we between 0 and 2 pi?
That's right. We're going to stay between 0 and 2 pi once around the unit circle.
Now these aren't related by our Pythagorean identity.
That's right.
And they don't have a common factor because secant is the reciprocal of cosine.
Oh, that's a good point. Do we want to rewrite it as the reciprocal? Would that help us to get them all in terms of just cosine? I remember that was one of your strategies.
Yeah, writing everything in terms of just the simple trig functions. So writing it that way, is that what you mean?
That sounds like a good start, because that way now we can just concentrate on cosine instead of having to worry about the secant. We didn't move the secant over to the other side because at that point we would have lost our 0. We like to keep 0 if we can. It's always helpful.
Handy. 0
Yeah.
is handy.
Now, how do we deal with a fraction in an equation like this?
I think a lot of our students don't like fractions, and they'd just as soon be rid of them.
Okay, well, let's see here. Could we get a common denominator, maybe to subtract the fractions?
Okay,
before
so we
get rid
can
of it?
combine it here.
Yeah,
We
there
can
might be
combine
a
it.
way to combine as well as clearing.
Okay,
There's
so
two
this
different strategies.
this is over 1,
That sounds good.
and so now it needs a cosine top and bottom in order to be.
That's right. In order to subtract 2 fractions, we had them practice on all that worksheet involving subtraction, and they had to get a common denominator. So let's do that. Did everybody follow? Mr. Murphy multiplied by the cosine on the top and on the bottom, and that's why he was able to get that common denominator. And cosine times cosine gave him cosine squared. On this one, we didn't have to multiply by anything, did we?
That already had the LCD.
That already had the common denominator, so we could keep it as 1.
Yeah.
Now, does this make things easier for us? It does help us get it down into 1 fraction equal to 0. How can a fraction be equal to 0?
Well, the only time a fraction is equal to 0 is if the numerator is equal to 0.
Oh, that's right, because you can't divide by 0, so it
That-
must be the numerator that would be equal
So
to 0.
should maybe make a note to ourselves never to let the denominator equal.
So we don't want cosine x to equal 0, otherwise this would be undefined and our secant would be undefined. So we're going to be looking for answers where cosine's not 0.
So, but now we're saying, let's just concentrate on the numerator.
Okay.
And figure out when that is equal to 0. And if the numerator is equal to 0, then the whole fraction must be 0, provided the denominator is defined.
That's right. This was a good strategy of getting that common denominator, because now we have something that's much nicer than 2 cosine minus 1 over cosine. We see a single cosine squared, and we're going to solve for it. Nice. I know where cosine squared.
Well, let's take the square root.
Ah, that's right. It's not just cosine x equal to a half on our unit circle. We're looking for the square root of a half.
And now that would be 1 over root 2. We've already done this.
Oh, yes, 1 over root 2.
But that can be simplified to root 2 over 2.
So we have our friend square root of 2 over 2. We've seen him a couple times, and here he is again. Let's see how many solutions we're going to have. In the first quadrant, we have our basic pi over 4, where both sine and cosine are square root of 2 over 2.
Same thing in the second quadrant.
Now the cosine's negative at 3/4 of pi. We go down to the third quadrant, and we have 5/4 of pi, where cosine is negative, and back to 7 pi over 4. So as we go around from 0 to 2 pi, we've picked up all 4 solutions for that section.
And we didn't need to worry about our little warning, but it was good to just bear in mind that we never let our denominator equal 0.
That's right. So we didn't pick any solution down here that would make cosine equal 0, just the ones that would satisfy the equation so that cosine minus the secant would turn out to be 0, 2 cosine minus secant. Well, I think we've got all the solutions there, right? Nothing else to do with this one. So you guys are in good shape here. We've been able to show you some strategies. We've been able to show you how to work with fractions again. That's an important skill. And all these things will be useful for you as you move forward in mathematics.
All right. Thank you, Mr. Haas.
Thank you, Mr. Murphy, and hope you enjoyed our lecture today.
Have a great weekend.